The last part of our remote sensing lecture unit is on aerial photography. So let's take a look at some of the concepts behind aerial photography and what we need to know about GIS as GIS users. An aerial photo could be just a black and white or color picture of an area on the Earth's surface. Oftentimes clouds are involved, either on print or transparency, right? That's a traditional photography. In the past, a film camera, now obviously digital, shoots a picture from a free flying platform. It could be an airplane, a helicopter, a small unmanned aerial system, or a balloon, or some other at some pre-planned distance above the surface. Now that distance becomes critical for scale, and I'll explain that in a bit. But aerial photography has been around for a long time. Originally, the first aerial photos taken from a balloon way back in the late 1800s. So it's not a new concept by any stretch of the imagination. So types of aerial photographies, two types, right? We have oblique and straight down or nadir photography. Oblique photography snaps an image from an angle, low to high, relative, or to vertical, but it's looking at things. You may have seen bird's eye view in Bing Maps. That's an oblique photography. Second type is oriented vertically. We sometimes call this nadir because that's looking straight down. You point the camera straight down to the nadir at the photo center point to show the surface from directly above. Most aerial photography that we use in GIS is from this perspective, obviously, because when we look straight down, we can actually map it, and the scale is not different from one point to the next across the image. So here's some examples. Here's an oblique photo looking across a scene. One of these days, I'll replace these photos with some from a drone, but that's looking down at an angle from a high point. And vertical photo, of course, looking straight down. This is an aerial photo, rather old, but taken straight down looking at the Susquehanna River in the Harrisburg area. And so that's nadir, meaning focused straight down. Aerial photos and scale are important to keep in mind, right? Here's a 1 to 100,000 scale. As we zoom out, we got a smaller number. Shows a larger area, if you remember from scale from unit 6, or 5, excuse me. And then all the way down to 1/4000, this is a large scale, right? The number here is this fraction, so to speak, is a larger. So now we're zoomed in and we can actually see individual homes and roads and even vehicles on the road. So the scale of an aerial photo is critical to our understanding and our being able to map it properly and accurately. What determines the scale? Well, I'm not going to have you memorize this formula, but you should know that it's a mixture of the focal length of the camera, and if you know anything about photography, that has to do with the distance from the lens to the film or the sensor, the height above the ground, above sea level, and the height of the camera. So at a 100 millimeter lens, at 1,000 feet up, you can actually work out to different scales. So 1,000 feet, 100 millimeters, that's actually 4 inches to 12,000 inches in this particular case. And when you divide that out, you get 1 to 3,000 scale. So again, the focal length, the height of the camera minus the height of the surface of the Earth that it's flying above. So this is essentially the distance from the camera to the ground divided by the focal length. And that actually, when you work that out, it actually gives you the scale of the photo. So depending on how high you're flying and what kind of camera you're using, your representative fractional scale will be different. As an example, in our drones that we use at the Harrisburg University program, we have a 20 millimeter camera underneath our Phantom 3 advanced drones. And depending on the altitude we fly or the height above ground level, that derives the scale. In fact, at about 150 feet, we get just over 2 centimeters per pixel as a what's called ground sampling distance. But again, let it be known that it's basically the focal length and the height above the ground that determines the scale. Just like the size of an image. If you zoom in and stand closer to something and take a photo, you're going to have a larger scale representing a smaller area. The National Aerial Photography Program was set up many years ago, and it still continues. And it's a jointly funded federal and state program to acquire 1 to 40,000 scale aerial photos of the entire United States every 5 years. It's flown at 20,000 feet, has a 6-inch focal length camera, and this other important concept, end lapped and side lapped. It's the idea is that as you fly over, you're taking a photo and you're overlapping the previous photo. 60% in the forward direction as you fly along, and then as you come back for a second pass, the edges overlap as well. Remember earlier I talked about ortho photos and ortho rectifying photos. The idea of the overlap is we're looking for the sweet spot, the middle part of each picture, because that's where our least amount of distortion occurs. As you get out to the edges of a photo, you start to get a little distortion. So here we're managing to keep the middle part of image 6, the middle part of image 5, the middle part of image 4, and we're keeping that. Allows us to get nice, accurate, and less minimal distortion in our imagery. Frequency of National Aerial Photo Program. This is up through the early 2000s, but it's indicating how often areas are flown. We have the same idea here in Pennsylvania with the PA MAP program that ran until about ended a little less than 10 years ago. It was a concerted effort to make regular flights over the state of Pennsylvania. So here are the digital ortho quads for Pennsylvania up through 1999 that were flown, all stitched together. Here we have an example of a U.S. Department of Agriculture 1 meter resolution. So again, each pixel, or each grid square is a meter by meter. And this is when LEAF was on. So this is actually color infrared. And in this case, we're representing infrared reflectivity in red colors. It's false color. Obviously, the world doesn't look like this. And then I mentioned the PA MAP program. Back in 2003, it was started. And they also created digital ortho quarter quads. And this is an example of that aerial photo right here. The PA MAP program produced ortho imagery up through and including 2010, and then was scrapped in favor of just doing things, one-off operations. Individual counties or cities would fly their own aerial photography. But you can see what parts of the state were covered when. This is important to know if you're looking at aerial photos of an area and you realize that maybe they're 7 or 8 years old. Lots of things could have changed in that time period. But the PA map ortho imagery was 1 to 24,000 scale, which meant that each pixel on the map was a 2-inch resolution, a 2-foot resolution, excuse me. So you could make out cars and things like that, but higher level of detail might have required a different level of imagery. And many times counties and cities would have their own aerial photos flown. But this was a nice concerted effort across the entire state to do it. Also with LiDAR. Now we won't talk about LiDAR too much in this class. It's light detection and ranging. It's basically an active remote sensing where you're shooting infrared laser beams down to the earth in sometimes as many as 100,000 pulses per second, and getting that reflectivity, the bounce back of that infrared laser beam to determine very detailed ground imagery and topography, for example, and surface models. This was run through the 2008, and so the last data we have for the state of Pennsylvania was finished in 2010. Other counties like Dauphin County, where Harrisburg is located, just had its own LiDAR data flown not too long ago, just about a year ago. Here's another 1 to 8,000 scale false color infrared. You can see a lot of reflectivity off the water here but you can also see where the forested areas are in the mountains. There's a valley here, so you've got some paved and developed areas. Notice the dark spots up here in the mountains. Infrared is an indication of plant health, and this imagery was taken actually during the time when we had gypsy moths killing trees up on the mountainside. So you can see areas where the trees were not as healthy because of that. Traditional aerial photography was kind of challenging, right? You had to bring in your images, do the ortho rectification that we talked about, make sure the scale's uniform across the whole area. It's expensive to fly. The camera equipment here in this right image, this is a $1 million Microsoft camera. It effectively has something like 120 megapixels because there are multiple sensors. This is inside a plane with the analyst running and keeping track of all the data that's being captured as they go along. Nowadays, we can capture information not from expensive planes and expensive cameras, but we can actually put them up in unmanned aerial vehicles like balloons, fixed wings, multi-rotor, single rotor, quadcopters, that sort of thing. So lots of ways of gathering data now with drones. So we can do our own remote sensing. Here's an example of Harrisburg University. This is a former student. We had a HD camera, flip camera, on the bottom of a balloon. So this was taken at about 800 feet up, and you can see how we overlaid these images and georeferenced them to City Island here in Harrisburg. So there's the balloon way up in the sky. There's just one example of 1,000-foot. Yeah, we actually put it up 1,000 feet. That's the max you can put up a balloon. We had a lot of kite string to fly that thing. And this is City Island, so you get the kind of resolution there. Nowadays, we're using drones, and so here's some drone imagery from 150 feet. So here's another former student. You can see this is where we were standing. This is our takeoff point, a big piece of plywood, and we're flying over a fence row. So drone imagery can be quite useful. So lots of ways of gathering aerial photos. I want you to be familiar with those so you understand the kind of data we can bring into GIS. So that ends our raster and remote sensing unit. We'll pick back up with the next one next week.